My name is Sergey Maschenko. I'm from SharkNet, Compute Ontario, Alliance, used to be Compute Canada. And today I'll be talking about how to profile GPU codes with Nsight. So here's the plan. I will briefly walk you through a few important points. For example, why do we need to profile GPU codes, where this can be done, and how. And I will end with some live demonstration of the tools. So why do we need to profile GPU codes? Of course, there is always a need to profile any computer code because we want it to be more efficient. And by the way, profiling means making the code more efficient, timing the code so it becomes better and better as we reduce the timing. But GPUs in particular are really sensitive about profiling for the reasons listed here. For example, GPUs are significantly more expensive than CPUs, and they are less available as a result than CPUs. And this trend will continue to the future for sure. There is also an important point that GPUs, the way and the reason they excel, because they sort of carved a niche for themselves. They are distinct from CPUs in their ability to run massive amount of small threads in parallel. And by massive, I mean hundreds of thousands or even millions. So CPUs don't do that well. GPUs are designed to do it very well. And even though GPUs become more and more general purpose computing devices, they still will keep their niche for sure, because that's what differentiates them from CPUs. And because of that, not all research codes and algorithms are equally well suited for GPU acceleration. So given that GPUs being more expensive, less available, and that not all algorithm or research codes are guaranteed to run well on GPUs. So what we have to do when we write a new GPU code or convert a serial code to GPU acceleration, we really want to start profiling the code from the very first GPU functions we create. We call them kernels. So very first kernel you create, you want to start profiling it. Why? Because you want to make sure your algorithm actually accelerates well on GPU, first thing, so you don't waste your time doing further programming. And second, the decisions you make at the very first kernel stage are often fundamental. So you decide about layout of your data structures, how much and when to move data to GPU from GPU. All these things are very expensive in GPU computing. And depending on whether you do the right decision or wrong decision, you either do a good programming project or you fail at some point, wasting your time. So given all this, GPU code profiling is even more critical than a regular computer code profiling. This talk will concentrate on NVIDIA hardware, NVIDIA GPUs, for the simple reason this NVIDIA is by far dominant in the ARC HPC GPU computing for a number of reasons. So AMD and Intel are trying to catch up, but they're way behind in terms of availability and how widely these GPUs are used for research. And as a result, I will be focusing on NVIDIA profilers, tools developed by NVIDIA to profile their own hardware. NVIDIA has been doing it for more than a decade. I'm talking about the tools. So some of the tools were already expired a long time ago. Some are expiring now. So I'll just briefly mention tools which are still perfectly usable up to a point, and they are installed on our clusters in our system. One of them is a very nice and simple command line utility NVProf. This is a function level profiler, so nothing fancy, no line by line profiling like Nsight tools can do. And it also works for both GPU and CPU parts of the code. And VVP is the graphical profiler, which is being retired currently. I would say at this point, if you're not familiar with either of these tools, even though they're available in our systems, unless you have particularly strong reasons to use them, do not learn them, because instead concentrate on newer tools, which will be maintained for a long time to come. And those newer, they're actually not new. Nsight has been around for a decade at least, or more than a decade. But now it's becoming the main or the only suite of profiling tools from NVIDIA. Originally, Nsight was given as produced as part of Eclipse on the Linux and Mac. This is IDE. And a bit later on was joined by IDE Visual Studio Edition under Windows. And relatively recently in 2018, NVIDIA decided to also produce standalone packages. For reasons which are probably I don't have time to explain, NVIDIA had to produce 3 different packages. Instead of 1 profiler, there are 3 Nsight profilers. Fortunately, for the purposes of our webinar for HPC/R computing Nsight graphics, the 3rd one is not relevant. This is more like for gaming development, etc. For computing, you only need to care about 2: Nsight Compute, which is a low-level profiler, and Nsight Systems, it's a high-level profiler. This is how NVIDIA describes the interaction between these 3 packages. Again, Nsight graphics can be ignored for the purposes of today's presentation. NVIDIA suggests the entry point should be around here at high-level profiler, Nsight Systems. And as you move along, you start profiling individual functions run on GPUs, kernels, and then you start moving back and forth. From my personal experience, I would actually recommend the other way. And this is due to the fact I already described to you. So when you create a new GPU code or you convert a serial code to GPU, what you do, you find the most compute-intensive part of your algorithm and you create your very first kernel GPU function. And you really want to profile it well, very detailed level. And that's when you make those decisions about structure of your layout of your data, etc., which are fundamental for the performance of your code. So you really want to start from Nsight Compute to have line-by-line ability to profile individual kernels, to squeeze out the maximum performance out of it. Once you converted most of your stuff to different GPU functions, then you start worrying about how they can run together asynchronously, so you save time of data copying, etc. And for that, you definitely need Nsight System. Also, if you start playing with multi-threaded CPUs, OpenMP or MPI, Nsight Compute will not help you. You need higher-level profiler like Nsight System. Now about where to run Nsight. So one possibility, if you have a fairly capable recent GPU inside your computer, you can install these packages yourself, or you can install the whole IDE, Eclipse for Linux, Mac, Visual Studio for Windows. A significant advantage is that you get not just profilers, but IDE, editor, compiler, debugger, all in one package. This seems to be very nice, but most likely will not work for you. Because when you profile your code for GPU, you definitely want to profile it for a very specific GPU you will use for production runs. And if the purpose is to run your code on one of the national systems, you really want to profile and run Nsight on one of the GPUs installed on our systems, which are either P100, these are older Pascal, Volta V100s, or newer A100s, Amperes on Narwhal cluster. I doubt very much your personal computer has one of those. So most definitely you want to run these tools on our clusters, on very specific GPUs. How to run it, I'll describe a few strategies, but I will focus on one particular, which seems to be the best overall. One possibility is these tools can be run as command line tools, and they can be even enclosed in a SBatch script you can submit as a job. It will write out profiling output, and then you can analyze that file either on a cluster, or you can even copy to your own computer and run locally installed Nsight tools to analyze the profiling result. But it's somewhat involved. So the best way is to run interactive GUI tools on compute nodes, allocated with special command salloc. You can use either X11 method for a graphical interface. This is much less efficient, so I will not recommend it. I will instead focus on VNC connections, running VNC connection on the compute node. This gives you the best performance, even with a relatively slow internet at home. You can still get usable connection, graphical connection to compute node. And just to help you visualize, this is connection which goes through secured SSH shell sorry, it's SSH tunnel. And it kind of goes from your computer to login node of the cluster and from there to compute node. So it's a fairly involved way to transfer graphical information, but using VNC, it's still most likely going to work well for you. But if it's too slow or sluggish, then as I mentioned, you can run command line tools on the cluster and then analyze them either on your computer or perhaps on the cluster offline. Now to the question of how to use any GUI tools and clusters, in particular Nsight profilers. I mentioned one method, X11 forwarding, which is less efficient. Prerequisite, if your computer is Windows, you need to install MobXterm because you need so-called X Windows server. And MobXterm comes with a prepackaged with X Windows server, and it's actually enabled by default, so you don't really need to do anything. If you're on Mac, you need to install free app X Quartz for the same purposes. If you're under Linux, you don't need to install anything. So visually, it looks simpler, X11. So the only difference when you SSH to cluster, you have to add -Y to enable X11 forwarding. And then when you allocate compute node on the cluster, you have to add --X11. Here, X is small. So it's simpler, but as I mentioned before, X11 method is slower. You can try it, and if it works for you, so you can use it. But in my experience, it's not very good. Instead, I suggest you try and just you use VNC for all your graphical user interface applications on our clusters. So here's step-by-step description. We have a wiki page about this. If you search for VNC Compute Canada or VNC Digital Alliance, you will find that wiki page. So I'll just briefly explain what are these steps, but then on the next slide, I'll show my own script I just created for this webinar, which should significantly simplify. So basically make it almost as simple as using X11. In any case, you need 2 terminal windows. So if you're running MobXterm, as I will be today, you just open 2 separate tabs. And one is the blue tab, let's say the other one is the brown tab. So in the blue tab or shell, you log into the cluster and then you execute your /hour command. By the way, do not add --X11. It will actually interfere with VNC. So do not use it for VNC connection. Once you're in the login node, let's say it's gra123, gram cluster, you have to execute this special command because this is a requirement for VNC server for the next command. So very first time, if you do it for the first time on a cluster, any given cluster, you do it by hand, manually, as described here. Because what's going to happen when you type VNC server, it will ask you a few questions. In particular, you will have to create a password and you have to type it twice. Fortunately, this is only has to be done once. And from then on, no matter where you log in on that cluster, it will never ask you password, but you have to write it down, of course, because you will need it later. So after that, after do it manually, next time you do these steps, you can use the script I described in the next slide, because then you don't have to worry about entering a new password. And then on the next tab, on your local computer tab, you don't log into a cluster, you execute this SSH command. What you're doing basically, it's called port forwarding. VNC server requires or talks through remote port, by default 5901. And then you want to forward it all the way to your personal computer, and let's say it's 5902. In very rare situation, if you use your own VNC servers, and more than one maybe, then maybe you'll have to change it. But normally this number can stay as is. This also typically the same. So the only thing you want to customize is the compute node. It has to match this compute node from your /hour session from the blue terminal, blue tab on your MobXterm. So you make sure this matches, and you have to provide -N capital L capital for this to work. If it doesn't complain, it just hands there, which means it's established the port forwarding. And that what you have to do, you have to install Tiger VNC viewer on your personal computer. So they're available for Windows, Mac, and Linux. Just the viewer. You don't need server, just the viewer. And when you launch it, it's going to ask you for destination, and your destination will be like this localhost column and then this number, which typically is 5902. So it may sound a little bit complicated compared to X11 approach, but it gives you significantly better performance. And as a bonus, if you do it once manually, the next time you do that, Let me show. This is the script I just created for this webinar and seems to be useful. So what you're going to see here, so you run the script, you can paste and copy it from my slides after presentation if you're interested. But basically you run it after you do salloc, you log into cluster, do salloc. Once you're in a compute node, you run this VNC script. It does the commands I just listed on the previous slide, export. It runs VNC server, but it also correctly calculates, captures what's the channel. By default, it's 1, but if it's taken, it can be 2 and 3. And then it calculates a remote port, which is by default 5901, but can be 02, etc. So, but it's correctly captured. And then it prints out the command for your local computer, for your second terminal. So it knows everything about your username, cluster name, and also compute node you allocated, and also remote port. So all of this is presented in a simple line, which you just highlight, paste and copy to a second terminal, and voila. And then you can use Tiger VNC viewer to establish VNC connection. All this will be demonstrated in my live demo, so it should become even more clear. All right, so what else to know about how to use profilers in all clusters? They become available once you load CUDA module. And we strongly recommend to always load the most recent, the newest CUDA module. We have lots of them installed. To see which ones are installed, you can run module spider CUDA command. And currently the newest is 11.4. So that's what you need to execute currently to get the newest CUDA module. Once you do that, you can compile your code and you can avail profilers, both old profilers like NVProf and NVVP, which is command line and GUI, and the current tools. So Nsight Compute comes as both command line, NCU binary, and NCU-UI GUI. And Nsight Compute, unfortunately, can only be used with Volta and newer. So it will not work on P100 GPUs. So if you need low-level profiling for P100, I'm not even sure if there is an option. I don't know how good NVVP, it's still usable, but I don't know if it does the same functionality as NCU. So that would be sort of the only recourse. Fortunately, the system level, high level profiler NSYS command line, NSYS-UI GUI version works on Pascal and up. So basically all the GPUs we have in Alliance National Systems, NSYS is usable. About compiling your code, you have to actually recompile your code for proper profiling with these tools. But the only thing you need to make sure you add dash line info switch to your NVCC compiler. And NVCC is the NVIDIA compiler, which becomes available once you do module load CUDA. Make sure your architecture you're compiling for matches the GPU you're trying to use, because profiling is highly sensitive on particular GPU version. So this is for Volta's capability 7.0. So that's why this is the architecture SM_70. For Pascal, P100 would be 6.0, for T4s would be 7.5, and for 8100s would be 8.0. Do not use -G. Some of you who may have already debugged GPU code, that's what you use to preserve source information, source code information, but you do not use it for profiling. Instead, use -line info because it's much more suitable for profiling. And before doing live demonstration, let me show you a few slides for each package. So Nsight Compute, this is the lower level profiler, comes as command line and GUI application. So if you want to run it command line version, let's say through sbatch, and then analyze it offline, you have to use command like this, NCU-O, then the name of the output file, and then pass to your code. Then you run it any way you want it, interactively or through sbatch. Once it's finished running, you can take that file and either analyze it right there, maybe on the login node or somewhere else, or copy to a computer. Then you can analyze using Nsight tools on your computer. So as I mentioned, I suggest this is the first step in profiling GPU code when you're trying to perfect performance of individual kernels. And that's its main task, maximize performance individual kernels. I will not even scratch the surface here with my presentation. You really want to read full documentation because so much more is possible with this excellent tool. There are like a zillion of things you can get information about. So please check that reference. And when you launch, run your code through this profiler, you will be presented with this default screen, and it's already overwhelming. And by the way, you can barely see this is actually just a fraction of the screen. You have to scroll down, and most of the items here are collapsed. You have to open them up, and then you'll see much more information. So it can be quite overwhelming. In this presentation, I'll just concentrate on a few basic facts about profiling so you don't get overwhelmed. And as I mentioned before, NCU is the kind of profiler which allows you to get line-by-line information inside your GPU code, which can be excellent. So you can actually see each line of your GPU code, how many registers it's using. And why it's important, modern GPUs allow you to use up to 255 registers per thread, which seems to be a lot, but in complicated codes, you may go over that. So there'll be some lines of the code when you can go over 255. It's not going to break your code, but it can become much slower because those registers will be moved, offloaded. We call it spilled into device memory, which is much higher latency. So it's going to be substantial performance hit. So this profiler gives you a convenient browsing ability to go to the most heavily used lines of the code, so you can try to optimize them. For really hardcore geeks, on the right side, by default, you also will see assembly code, and you actually will see the individual lifetime of your register, etc. So extremely low-level information. I'm sure 99% of you will never ever need to touch, but just for your information, it is available. And a couple of words about Nsight Systems, the other profiler. Similarly, it comes with command line tool and sys and GUI and sys-UI. If you want to, again, to run it through SBatch, record the file, and then analyze it offline, you have to say nsys, and there is special command profile, and then -o and output. So unlike NCU, where just NCU-O, here you say nsys profile-o, and then path to your code. I suggest it's not maybe last, but it's a second step in profiling GPU code, and then you probably end up going back and forth. And Nsight Systems is for fine-tuning interactions between things which presumably at this point are fairly well optimized, like kernels, mem copies, also CPU threads, multiple GPUs, and the power comes in when it comes to asynchronous execution of asynchronous elements. For example, you can profile multiple things running on GPU, as I will be demonstrating with my example code. You can run memcopy in parallel to kernel. And that's one of the important tricks used in GPU codes to improve efficiency of the code. Again, I will not even scratch the surface in terms of feature description, so please check the full documentation for all the details. And this is a typical screen you'll be seeing soon in live demonstration. So you don't see now the line-by-line profiling. Instead, you see a timeline, and you see a bunch of things running along sort of timeline in terms of CPU threads and GPU threads, etc. So I'll be explaining that in my live demonstration. All right, so I think we reached the point we can do live demonstration. I first will show you how to establish GUI connection to a compute node. So I'm under Windows Computer, and I'll be using MobXterm, which is excellent tool for anything to do with Alliance when you are a Windows user. And I'm going to start local terminal. And I'm going to right click and duplicate, because as explained, we need two tabs to establish VNC connection. So first I have to connect to a cluster on my first tab, and I'm going to be using Graham cluster for today's presentation. So I'm going to use my my special device for authentication. So I'm in a login node. Now I will run my shour command. It looks a bit different from what you normally use because I made a reservation for my presentation. So I will be using this command. Hopefully it will give me instant access to a V100 GPU. Yes, so I have access to the full node. It has actually 2 GPUs. I'll be using just one. So I'm gonna clear the screen so it looks better. So, and as described on my slides, I showed you before, I have to run a few commands. Once on a compute node, By the way, I can double check that indeed it is compute node, which does have GPU, and you see there are two V100 GPUs available here. So I will be executing the script, which perhaps you can even copy yourself. I'm not sure about my permission, but they are located right here on Gram. So as one of my slides shows, this is the script. I already ran VNC server before on Gram, so I already created password. So it's perfectly fine for me just to execute this VNC script. And the beauty is I don't have really to tinker too much with it. This is the command I need to execute. It provided everything I need to know. It's all in the available form. So all I need to do is just paste, Ctrl Insert to paste, and then go into my local second terminal, which is a local computer. I did not log into cluster. I copied that command. I'm executing. It asks me to authenticate myself, and then it hangs. If there are no error messages, which means it worked correctly. So now I establish port forwarding from remote 5901 port on this compute node all the way to your computer where it will be presented as this port 5902 and all the way through highly secure SSH tunnel. All right, and at this point, we're actually done with Mobile Store. We don't need it anymore. We instead will be using Tiger VNC Viewer, and I installed it already, and it remembers the last command I used, and this is what you'll be using pretty much the same command, localhost 5902 connect. Ignore this message, this connection is not secure, because from VNC viewer point of view, we are talking to a local process, a local VNC server, which it thinks is insecure. Instead, we are talking to port, which was securely forwarded all the way from compute node. So in fact, the connection is very secure. So ignore this red message. Now you have to type the password which you created on that particular cluster first time you run VNC server. So, and almost instantly you present it with graphical desktop, which as you can see, can probably barely see, it is on compute node. It's all the way on compute node, and you can run all kind of graphical GUI application. What I normally do right away, right click my mouse, open in terminal. So I like to have my terminal here. And again, you can see I'm on a compute node. I'm gonna go in the folder created for today's presentation. There are a couple of codes I'll be demonstrating. And first thing we wanna do, we wanna module load CUDA, the most recent 11.4. Oh, sorry. I'm looking into the future, way into the future. So on 11.4. So now I can compile. I already compiled the code, but I want to show how I do that. NVCC and -02. This is optimization for the CPU part of the code. Don't forget arch equal to SM_70. It's Volta, so it's 70. And of course, line info. I told you it's important. And then we're going to be profiling first a reduction code. And I'll just show in a second what it does. So that's what I'm going to do. There are a few other codes which are already pre-compiled. I will not be repeating it today. I'll be just using the binaries. So this created the binary. You can already run it. You're on a compute node with the cluster, sorry, with the GPU. It's a very short GPU code, and it has internal timer, which I just put there by hand, and it's already very short, 5.3 milliseconds, but still we want to optimize. I'll be showing two versions of this code. And to get there, I want to switch back to my slides, a couple of words of this reduction code. So what it does, as the name suggests, it does a reduction operation, in this case, addition. So it adds up elements of a long vector on GPU. And I have two versions. The first version uses a very slow method, serialized summation using atomic add function. Why do I need actually to do some tricks? The problem is reduction is a little bit tricky to do in parallel because it breaks pure data parallelism. So you have to do some tricks. The most primitive trick is to serialize computation. And CUDA gives the ability to do that through atomic add function. But imagine you adding up millions of numbers. using one GPU core at a time out of thousands on the GPU. So imagine how inefficient it is. In fact, the code is much slower than equivalent serial version running on the CPU. Instead, the proper solution is to use the second version of the code, which uses the parallel summation using so-called binary reduction. I think I have time just to briefly explain what binary reduction is, why it's so powerful. So for simplicity, imagine you have only 4 threads, GPU or CPU, whatever, and they have different colors, purple, blue, green, and orange. And let's say you need to add up 8 elements of a vector. So in a binary reduction algorithm, you go in stages. So first stage is to divide by your vector in 2 halves, left and right half. And then you let your 4 threads to do things simultaneously, concurrently. So purple thread takes leftmost element on the first element on the left side and the first element on the right side and adds them up and then saves in the first element on the left side. At the same time, blue thread does the same with the second element, green does with the third, and brown does with the 4th element. So all of this happens simultaneously in parallel. That's where the power comes in. So the next stage would be to divide further into 2 halves and you continue this process. At the end, your final result is the leftmost element of this vector. So you can see not all threads are busy all the time. So number of threads doing something is reducing with time, but still using a lot of parallelism. So in fact, this approach is much faster than serial computation, serial reduction. So serial reduction scales as n, where n is number of elements, and binary reduction scales as logarithm base 2 of n, which is much, much faster, as you will see from my code execution. So I think that's all I want to show for now. Switching back to my VNC session. So now I'm going to launch NCU-UI. So I will only be demonstrating the graphical version of Nsight Compute. So as you can see, it works fairly nicely and smoothly using VNC connection. Would be much more sluggish if I used X11 connection instead. So right away, points of notes for serious work on a large project, you want to create new project. Instead, for quick and dirty demonstration, you can use quick launch. The difference is you will be asked 2 questions fewer maybe. So it's almost the same, just less things to type in. So I'll be doing this. Basically, quick launch means you create a new project using some default settings, quick and dirty. So what you have to do here, it remembers my last commands I used, but you would have to basically click here and find the binary on our cluster, the one I just compiled. I know it's reduction. This is the name. So by default, this is working directed. And then you have to create and give name to output file. Let's call it reduction. Another important point, before you do the launching, you want to check sections. By default, I don't even remember which ones were enabled, just a few of them. What I did, I went ahead and enabled almost pretty much anything I might need, which means amount of information can be quite overwhelming, but don't worry, I'll be focusing your attention on things which matter. But I basically maximize amount of profile information available. I only excluded NVLink stuff. NVLink special hardware which connects multiple GPUs. I don't think we have it on Gram, but even if we do, we're not going to be using multiple GPUs for this presentation. So, and then all we need to do is click launch. This is a short code, so it will be a fairly short run. And that's the screen which I showed you before, which can look overwhelming. You might not even see the details too well. This is 4K. So as a recording, you might go back and check on our YouTube channel. But I will just focus your attention on a few things. So first of all, and as usual, I forgot to mention one thing. So actually, there is a choice. One screen before that, there was a choice before I click launch, whether to run it interactively or profiling session. By default, it's interactive, but I find it more useful to do the profiling. So what profiling means, you run the whole code, you collect everything you need, and then you can go back and forth between all the kernels and analyze things. I find it just more useful. Interactively, you basically click, 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 you go from one kernel to another kernel to another. I just find it not particularly useful. It's time consuming. So next time I run the code, I will hopefully remember to emphasize that point. So this is using non-interactive mode of this profiler. So what you have to pay attention, what you're looking at, it's a details page. There are also other pages, summary. Summary, for example, gives you a list of all the kernels. This code has two kernels. One is a tiny, one thread only. The other one is a larger. So going back to details, but you can also choose particular kernel you're looking at in this drop-down menu. So this is the very first init kernel, which I don't care about. It's tiny kernel. Instead, this is my main compute kernel. And so pay attention to yellow signs. These are warning signs. Something is not right in terms of efficiency. So they're always there for a good reason. But my warning is they not always tell you the possible culprit. So in this case, it detected correctly that exhibits low compute throughput and memory bandwidth, but it thinks it's typically indicate latency issues. But I already told you the actual issue is the fact that we use an incorrect atomic reduction, which in some sense it is latency because all the threads wait for a single thread at a time doing this calculation. So in some sense it's latency, but not very obvious, right? So sometimes you have to use your judgment. Don't take it literally, all these suggestions. But now pay attention to the numbers you see here. So it shows you throughput in terms of theoretical 100%, and you can see it's less than 0.5% we are using of the GPU in terms of compute. It is extremely inefficient GPU code. In terms of memory throughput, it's 1%. In terms of cache throughput, it's 1% or less. So obviously super inefficient code. So let me demonstrate how efficient version of the same code works. So what you can do, you can add either new projects or you can run multiple times the same project, and we'll keep creating new tabs, which you can click back and forth to analyze and compare them. So I'm just going to click on new project. So now I'll be analyzing my second code, which uses binary reduction. I'm going back. I'm going to go to reduction 2. And that's the thing I forgot to mention earlier. So by default, it runs in an interactive profile, which I find more time consuming and less useful. So instead, what I do, I click profile and then it remembers it. So I'll run it in a profile mode, which means it will run the whole code and that let me analyze any kernels I want. So now it opened a second tab and I want to make sure it's the same kernel, my kernel. And what a world of difference. Look at it, look here. Compute throughput, it's almost 100%. So we're almost utilizing 100% efficiently our GPU. Memory throughput, 78%. L1 cache, 2%. Again, compare that to these, which are 1% or less. So we see a dramatic improvement in terms of efficiency. And in fact, now we get, it's not a warning, but just a note. We are into extremely high throughput node. That happens when it's more than 80% of code efficiency achieved. So I don't really have time to go. There is so many more things you can walk through. For example, and these are collapsible. Click, and there are more. Some of this information is graphical, extremely high detailed level. So instead, I'll show a few other useful features. So once you open a few versions of your code, it becomes hard to compare the numbers, right? You have to click back and forth and back and forth. So this tools allows this easy way to compare them. Choose a baseline report. Let's say the slow report is going to be my baseline. And then I'm going to click here, add baseline. That's all. Once I'm done, I can clear baseline if I don't like it. So now we see not just the actual numbers, but relative numbers. In this case, it's all 0%. If I go to my next tab, you'll see the improvement due to better algorithm. And there are 23,000% improvement. So it's actually even hard to read this number. In more normal, reasonable situation, you will see +10, +20, so which means you're on the right track. But here's a really extreme example, how much more efficient code you can achieve. And one more final thing I want to show you in Nsight Compute is line-by-line profiler. So for that, you have to go to this drop-down menu and choose source code. And if here you don't see the source code on the assembly code, which means you forgot to add dash line info during compiling of your code. Here I didn't. I don't care about assembly, so I'll choose in the next second menu just the source. And so what I'm going to do, because I enable all the sections, remember before clicking launch, there was a way to choose how much profile information to collect. I collected everything possible. That's why things I can show for each line of the code is stupendous. You can choose or look at all of the statistics. I just want to show live register. Remember I mentioned to you, live register is important because once you're over 255, you start losing efficiency. Now, once you chose which parameter I'm focusing on, you can use this navigator. This will take me to the line with the highest value, and highest register value is the worst. So here's my CUDA code, and the highest value is 8. 8 is very small. So you remember 255 is a critical value. This is just 8, nothing to worry about. But in a realistic large GPU code, you will see large numbers, definitely. GPU registers are extremely fast and extremely scarce commodity. And in a realistic code, you will start seeing problematic lines of the code. Or then you can do, for example, navigate to the next higher level, and then next higher level. And you can go to the lowest level, which is only one register when you hit return. So, and of course, there are many, many more things you can look for, cache, warp divergence, and lots of interesting, like here, divergence branches. If there are warp divergences, for example, you can find the line where it happens at the biggest level. Not surprisingly, warp divergence happen. For those who are not familiar with CUDA, sorry, I just, for these technical terms, but basically when you have if statement, while statement, that's where typically you have some inefficiency due to threads within a warp not doing the same thing. We call it warp divergence. Anyway, so before going even further into technicalities, so I want to stop this tool, and let's talk a little bit about the second tool. I'm gonna not save it. So let's now talk about Nsight Systems. And remember, I told you Nsight Systems, I would use it second after optimizing my kernels when I start introducing asynchronous behavior. So let's discuss a situation, a code example when asynchronous behavior would be useful. So I'm gonna go back to my slides. My second example for Nsight Systems, it's called stage copy compute code. So there are two versions of the code. The first version of the code first copies a long vector to GPU, then carries out independent sort of pixel by pixel computations of on that elements of that vector. The second version hides some of the costs of copying data to GPU. And for those who already did some GPU programming, you know the number one target for optimizing your code is to minimize amount of data you have to move to GPU or from GPU, because it goes through very slow PCI bus, and it's typically the largest, most serious bottleneck for your GPU code acceleration. So to hide the cost of the moving data, a logical thing to do is to copy and compute in parallel, because these are independent computations, so pixel by pixel. For that, you have to use explicitly two GPU streams. So this is the solution number one, large copy followed by large execute. Instead, what we do, we split up our long vector in a bunch of smaller segments. Then we copy first segment, and we start processing the first segment while copying the second segment, and so on and so forth. So most of the time, you'll be running things twice faster because you'll be copying and computing simultaneously on the GPU. So theoretically, you can speed up this code up to 2 times. More realistically, maybe 65, 70% is maximum we can achieve. So let's test that code using Nsight Systems. I already have it compiled, and I have 2, in fact, 3 versions. If time permits, I'm going to show all 3 versions. So first is stage, it's just the original version. So I'm going to do nsys-ui. So this is Nsight Systems tool, and I'm going to load my first binary, staged. And so you will see a window like this. First thing you have to do, you come here, it says select. That's what you have to do. You click on select, and that it gives you some option. Unfortunately, it doesn't seem to have a file browser, so you actually have to type by hand or paste and copy the name of the binary. Let's say it's staged. And also the working directory. I'll just copy it for the future. So so there is no file browser. You actually paste and copy it here. That's basically it. And because we only care about CUDA profiling, so this is the one I want to enable. But just to give you an idea, this is a powerful profiler, system level profile. You can do OpenMP, you can multiple GPUs, GPU context. You can collect GPU metrics, but apparently not even on Volt. I think only Ampere can let you do that. There is maybe if you do accelerated graphics, but yeah, these are the main things. Or you can even do MPI. So here's the MPI version, and you have to click and then just select MPI. And within each context or with field, you can choose subfields. In particular, if it's OpenACC, it's also allowed to, you can use this profiler for OpenACC. You have to enable that. If you profile in special libraries like QBLAS, which is linear algebra CUDA library, or QDNN, which is a neural network library from CUDA, you have to enable those here. GPU memory usage, it's expensive, so usually it's off by default, so you have to enable it here. So once you do all of that, then you click Start. So here there is no interactive mode, it's just profile mode. It's gonna run your whole code and then present it with this timeline. Most of the stuff I don't care about, the system level stuff, threads, I'm gonna hide them. I wanna focus on CUDA. And the actual CUDA is a small fraction of this code execution because this is a very simple test code. So I click here and then use Control mouse wheel to zoom in, because I'm only interested in this information. So let me zoom in all the way. So, oops, okay, I have it here. So as you can see, I have kernels and I have memory copy. Remember my simple version of my algorithm? I have one large mem copy followed by one large kernel, which is perfectly fine. Except that, as I said, you still can accelerate by almost factor of 2 if you manage to do these things, two things concurrently. Here we don't. We have one large mem copy followed by large kernel. In my second method, the second version of my code, so I go here, File, New Project, and click Select, and here I have to say Stage 2. This is the good version, and then I just copy the working directory. It forgot about what I'm doing, so I have to enable again. I'm collecting CUDA trace, Start. So as before, I don't need this. I want to see CUDA. Right away, see a difference. There is not actually 3 different streams: default stream, stream 14, stream 15. So let me zoom in. And you already can see it looks quite different from the previous picture. So whereas in the past, in the previous version, I did one, it's still available here, one giant mem copy followed by one giant kernel. Instead, I have only the very first segment is copy, and then I run things concurrently. I run things mem copy in one stream, and I run kernels in another stream. So you can see there are 2 streams, and mem copy is done in one stream, and kernels in another, and they're perfectly concurrent. They run in parallel. If you hover the mouse over the kernel, you see some details. For example, runtime is 700 microseconds. If you hover over the mem copy, it gives you detail about memory. Very important, look at the 4th line. Source memory kind, it's pinned memory. I have to give just a bit of background here. To be able to do this concurrent operation, the GPU, to be able to use streams, more than one stream, and we need 2 streams. One stream is for copying, the other one is stream for kernel execution. You want to make sure all the data you allocate on the host, on CPU side, is allocated not through malloc standard method, but through CUDA host malloc. It's a special CUDA function which allocates it on the host in such a way that it is, first, much faster to copy to GPU. And secondly, it can now be used for multiple streams. Let's say I forgot to do that. So in this version of the code, I'm using the proper CUDA malloc host, and it does the right thing. You can see memcopy and kernels, they're perfectly concurrent. Let me try just one more thing, code. Let's say I mistakenly used standard malloc. I did not use stage 2 band. This is the version of the code where by mistake use standard malloc. I did not use CUDA malloc host. How it's gonna change the situation? This is the very final thing I'm gonna show today. So again, I only interested in CUDA stuff. I'm gonna do zoom in here. So you can see two important differences, which both result in much less efficient code, just compared to the proper solution. So first thing so kernel length is the same in both. So in the proper solution, the memcopy length is the same as kernel. So that's why they're perfectly sort of run in parallel, very efficient. Here, the green parts are much longer than kernel parts. Why? Because my memory is not pinned. I use standard malloc. And that's why copying takes much longer, by a factor of 2 or longer. So that's big inefficiency. Second, in the efficient code, there is essentially no gaps. Kernels and memcopy stuff, they start essentially simultaneous, and there is no really gaps between memcopies. Everything runs smoothly in parallel. Here, there are substantially bigger gaps. Memcopy does not start with my kernel. And the reason for that is because I used non-pin memory, which is pageable memory. I mistakenly used malloc instead of CUDA malloc host. And that's why they're not truly concurrent. Memcopy and kernel, it breaks my multi-stream performance on my GPU. So this profile allows me to almost instantly see what's the issue and go back to the code and fix that. And I believe that's all I am to say today about these tools. So I'll just switch back to my final slide. And thank you very much for your attention.